Like a binary SS tree, the worst time complexity is big of n. To reduce this time complexity, there is the different variants of the binary SS tree has been introduced. One such a tree is the AVL, the red block, and B plus tree. Then, so let us see the one more approach, or one more the variant of the binary tree. So it is called as the split tree. The split tree. So the split tree, which reduces the time complexity from the big, that is a big of log n to big of one, big of one. So that it is going to reduce the time complexity from so log big of log n to big of log n, big of one, big of one. Now let us see like how so this split tree reduces the time complexity, and we'll see what are the different operations carried out in the split tree, and we'll see the examples. What are the rotations? What are the characteristics of a split tree? So this class is about this. In this class, I'm going to discuss about the split tree, starting with the definition, the split tree, then followed by different operations performed on the split tree. So then we'll see the time complexity of a split tree at the later stage. So yes, so let us take the example. The example is, so here is a say the 10, and so it is a 7, then it is, so here is it's 20, then so here is so 30. This is the one example, of so the binary search tree. So please observe that here is the so when the binary search tree is given, binary search tree is given to search the element, any particular element. So now as you know that you have to start with the root, then so compare the root element with the element we searched. If it is less than, we're going to traverse towards the left. If it is greater than, then you traverse towards the right. Okay, so that is the common procedure we'll adopt in binary search tree. Now, now look at this here. The AB and the red block and it's a B plus tree are the variants of the binary search tree. So how they are different from the binary search tree is by they're going to place some restrictions. By restrictions, the AB tree places some restrictions on the binary search tree such that the balance factor means here the height of left subtree minus the height of right subtree should be less than goes to like, so the value should be either it is a -1 or 0 or it's 1. So that we know that we studied it is a balance factor, the balance factor. So the balance factor, it is either it should be 0 or it can be -1 or it can be 1. This is the conditions I'm going to put. So in the similarly now red block tree also explicitly say some restrictions. The every alternative nodes must have different colors. And so there are many restrictions, like the leaf node should be a black color, like the leaf node color of the leaf node should be in the black. Like so in this way, it's going to put some restrictions. And similarly, it is a so the B plus tree also put some restrictions. So here also like here, but in case of the split tree, it doesn't say any the explicit restrictions on the binary search tree. The split tree is a self-adjusted binary search tree, which does not explicitly say or it does not put the explicit conditions for the balancing the height of the tree. Okay, it's a, in other words, you can say it's a specific type of binary search tree in which we're going to perform the operations So like it is the operation on the element will rearrange the tree so that the element is placed at the root of the root portion of the tree. So that's one definition. I repeat once again. That is, the SplayTree is a self-adjusted tree. The every operation on an element rearranges the tree so that the element is placed at the root portion of the tree. So this is one definition. So there are the various definitions are available. So one such definition just I told that it is a self-adjusting tree, and we're going to perform the operations, that is a rotation operations, such that the element is always placed at the root portion. So then one more definition say that it's the balanced tree however it does not enforces the explicit rule to maintain the balance. So in place of this, the explicit rule, it applies certain moves to the root operation. So called as the spray. After every access, in order to keep the access tree is a balanced one. These are the definitions. Okay, we have. So let us see, like, so these are the theory, and let us see with examples how these definitions are valid and why you have to do the different rotations. So that I'm going to illustrate you with examples. So let us see, like, so I'm going to write a definition. So definition I'm going to write here. So the definition say that, so just for you, it is, so right once again, it is a balanced as a tree. So but there is the however, so it does not so enforce the explicit rule to maintain the balance tree, to maintain the balance. Okay, that's the one definition. Okay. So in place of this, it applies some returns a certain moves to the root operation, and that is called as the splaying. Okay, so the splaying allows us to guarantee the amortized running time for the insertion, deletion, search. So all these operations are carried out on the binary search tree. Yes, so let us just go for the directly with examples so that it's easy to understand. So rather than talking about the theory, okay, let us see the examples. So yes, I'm audible to you. Yes, I'm audible to you. Okay, so let us continue our discussion now. So here is the one example is, say, the binary search tree. It is the some example. Yeah, this is the one example. So it is the elements are, so these are the elements, that is 5. These are the elements. So please look at this. Now to find, or to search to find the element 3, or to say it is the search the element 3. So I have to search the element 3. Okay, the element 3 is a left side of root node. The 3 is a left side of root node. So like, please observe that. Now in the SplayTree, as I told, it's a self-adjusting tree. It does not put any restrictions on the balanced but it performs some operations. What are the operations it does performs? So when you want to search the element, say the element is 3, element is 3. So that is in the SplayTree. So the element you want to search should be at the in the SplayTree. The element you want to search should be at root node. So it should be at the root node. So like here the now element is at the the element is a left side of the root node, correct? So now the SplayTree, what are the element you want to search? The example element you want to search is 3. So that should be at the root node. That should be at the root node. So to make this the element you want to search as a root node, you have to perform some the operation. So that is called as it is the rotations or a move operations. So you have to perform that is, so like whatever the element you want to set, the element must be at root node. So at the root position. So for this, so you have to perform some a move operation, the move operation or say rotation. So like now the first rotation I'm going to introduce here is a zig. So the zig rotation are they a zig rotation or a zig move or it's called as the right rotation. There are various names for this. So one is the right rotation or the zig rotation, or it is the various moves are there. It is the various names of this zig rotation. This zig rotation or rotations. So please look at this. The element you want to search, say it's X. And so the X is the element you want to search. X is the element the X is the element you want to search. Element to be searched. So now, so what you to do, like, so next you have to say that whether X as the parent, whether X as a parent node. X as a parent. So if X as a parent, so then perform zig rotation. So perform zig rotation. See X as a parent, and where is X? So X is a left side. That should be remember. So then, so if X is a left side, so if X is a left side, so X is a left side, so then you have to perform zig rotations. In the same way, if the X is an element to be searched, okay, element to be searched, then the X as so X has the parent, X as a parent node, and so then perform jag rotation. So like this jag rotation is performed when if so X is a right side. See, remember this is a condition. If X is a left side, then you perform the zig rotation. If X is a right side, then you perform the jag rotation. Okay, those are the things you remember. So these are the conditions it says. Okay, these are the conditions it says in the SplayTree. Okay, now like with respect to this example, so here if this is the element you want to search, so therefore you have to move this element to the root position. By doing this, what happens here is, so the element 3 is rotated or move towards or move over the root. We'll say in general it is say X is the element and Y is the parent of X, and so there is a Z. So like this is the tree. Suppose the X is the element you want to search, and for that, so there is no y is in a parent node, and so the z is a node. Z is a chain node of the x. So then you have to perform a rotation that is called as a move x over y. It is called as the move x over y. Remember that it is move the x over y. The move x over y. So by doing this, like now, so the three will be there's a root number 3 will be in the root node. So then, so once you do this, that's once you move the x over the y, so obviously this 5 will becomes a child node. The 5 becomes a child node, correct? So y becomes 5 becomes a child node, and 6 is also a child node of the 5. So then, so here is now the 2 is left side, because it was earlier it's also it is left side. So now also it is a left side. But after that, it is the element 4, it is a right side of 3. It's the right side of 3. So therefore, so this 4 has to be moved towards right side of 3. So right side of 3, and so here it is placed. Okay, so this is you're done. This is the move you're done. So that is called as a jig rotation. It's a jig rotation. Do you remember this? Okay, remember this. So this is the first rotation because as it is a jig rotation. So or is also called as it is right rotation, a right rotation. Okay, so this move is it clear to you? Is it clear to you? Is it clear? Do you understood this? No response. Yes, shall I proceed?
Yes, sir.
Understood
Yes,
this?
sir.
So you want to repeat once again? It's okay. So I just summarize once again. Like whenever in the split tree is a self-adjusted tree in which so the like so so any operations you want to perform, you have to rearrange the elements. Rearrange the elements of a tree. So how you have to rearrange such that the element you want to search or element you want to insert or element you want to delete should be at the root position. So in order to perform this, so there are various moves or there is various rotations. One is the jig rotation, is also called as a right rotation. So this jig rotation is applicable when the x is element to be searched and x has a parent node, and then perform the jig rotations. So that means when x is a left side. So in the similarly, like there is another rotation called as so a jag rotation. The jag rotation. So jag rotations will be performed when x is an element to be searched and x is a parent. In particularly, x is a right side of a parent, and then perform the jag rotations. So for this, to like so the example we've taken is, so this example, so element you want to search is 3. So this element is rotated or it is moved to a root position. In other words, it is the x is moved over the y. The x is moved over the y. So when you perform this x move over the y, so this element 5 is pulled down, it is pushed down, and 3 is placed onto the root position. So now resulting matrix, the binary search tree is shown here. So this operation, this tree is obtained by doing operation called as jig operation. Okay. So if you understood this, next let us go for next one. So next one is like here is the same like here. So here is the element. So is the element is 3. This element is 3. The element is 3 that is present in the root node. So the element is the present in the root node, and so for this, let us say now, like you want to find or you want to find or you want to search the element. You want to find or search the element. Say element is 5. The element searched is 5. The element is searched is 5. This is the element is present. So here the element to be searched is a right side. the element to be searched is the x, and x is the right side of y, the right side of y. So for this, you have to rearrange the elements of a tree in such that, so this, the element to be searched, it should be placed to the root node, to the root node. So, and so after rearranging this element, so the element is placed in the root node. So now let us perform the check operation. Why you to perform check operation? Because the element to be searched is present. The element to be searched is a right side of the parent, the right side of the root node. So then we'll perform the check operation, the jog rotation, to make this x as the root node. So by doing this, so like we're going to get the binary tree with a 5 as a root node, then the 6 is a right side. So then it is, so 3 is a left side. So then it is 2 and 3 are the left side and right side of this node 4. Okay, so this is the what we got. So understood this. Here we performed left rotation. We have performed left rotations. Okay, we performed left rotations, or we performed a jack rotation to make this the element to be assessed as a root node, as a root node. So now, so like see, when you try to set the element 5, the obviously the time complexity for searching the element is 1. Obviously the time to search the element is 1 because the element is present at the root node. The element is present at root node, so therefore the out of the time complexity to search the element is 1. So this, like you are reconstructed, or we rearranged the binary search string by using a rotation. So in this particular, we applied the jack rotation to get the element to be searched at the root position. Okay, so understood this. So now shall we go for next one? Next rotation. Yeah, next one.
Yes, sir.
So,
Yes, sir.
yeah, okay, fine. So the next rotation, rotation that is performed in the SplayTree, it is a zig rotation. So let us take the example. Here is an example which consists of the different nodes, in the binary search tree. So it is the same example which I considered in the previous one, I consider here also. Okay. So first, I'm going to define you, that is what is the zigzag rotation. So please observe that here, when you perform the zig rotation, so a zig rotation, so like here, so perform the zig rotation. So zig rotation. So perform zig rotation. So perform a zig rotation. So when you want to perform means, so the so this is applicable when the x is the element space test. The x is the element to be searched, and the x has the parent, the x has the parent, and x has so grandparent. Okay, the grandparent. So then you perform the zig rotation. So perform zig rotation. So what is zig rotation means? It is perform the zig rotation when the element possessed as the parent node, and also the x has the grandparent node. Okay, so with respect to this example, so first let us take the example. Here is the example is So it is example is, so example is here. The first here is the here is the next here is the x. Yeah, okay, I'll take this here. Now here is this is the x, and it is a y, and it is z. This is the general one, general one. Okay, here the x is element recessed, the x is element recessed, and x has the parent. This is the element you want to search. This is the element you want to search. This is the element you want to search. So for this x element, we got y as a parent. Y as a parent. So then, so this x as the grandparent. So this is the parent. Then, so the z is the grandparent. So when you do this, like, so the z is replaced with x. The z is replaced with the x, and so making y a child of x. The y is the child of x. Y is a child of x. Y is a child of x, and the z is a child of y. That is the child of y. It is y. So these are the things here. X is element to be assessed, and x has the parent node, and x has the grandparent. So then in the zig rotations, now the x replacing this x, replacing this x by so replacing this z by the x. Now make this y as a child of x and make the z as a child of y. Okay, so this is the operation you have to carry out. So now here is you want to find out, that is here you want to splay, or you want to splay this two element 2. So this is the element you want to splay. So this is the element you want to find such. So here is the x, and here is the y, and here is the z. So x is a parent, x is the element to be searched, and y is a parent, and z is the grandparent. So for this example, as I told that, so the z is replaced by x. The z is replaced by the x. Then so now y is a child of x. Y is a child of x. So that is, so 3 becomes child of x. 3 becomes child of x. And so z becomes a child of, the z means it is a 5. So now it is child of y. So it is y here, and it is z, and it's x. Okay. So now what we've done is replace this the z by x, replace the z by x, and make the y as a child of x, and make the z as a child of y, that we've done here. Okay, next. Now, so now look at the node x. The node x is a right child of 5. So therefore write this 6 as a right child of 5. Then the node 4 here, it is a left, yes, it's a right child of 4, a right child of 3. A 4 is a right child of 3. So therefore so now it is the right child of right child. So right child is already, there is a 5. So therefore, so the 4 is placed here. The 4 is placed here. So this rotation is called as, it is the zig rotation. So it is called as the zig rotation. So I just summarize once again the zig rotation. We perform zig rotations when the x is an element to be assessed, and x as the parent, and x as the grandparent. So then we perform the zig rotations. So in the zig rotation, So the z is replaced. The z is replaced. The node z. What is z? It's a grandparent. So replace this z by x. And y is a parent. The parent y. The parent y. So the parent y. So is replaced. The parent y is a child of x. And z, it's a grandparent, is becomes a child of y. Okay, so if you do this, like these are the steps to be followed in the zig rotations. Okay, so now, so we got the element, that element research is at the root position. Now we can search this element, so that time property will be, it is big of one. So that is, so by doing this, we reduce the time complexity, but the complexity is you to rearrange the elements to exist. So every time when you want to perform the display operation, so all the elements of a tree are rearranged. Okay, so that is the one drawback, but advantage is you are going to place the element you want to find or element you want to search is placed at root node. Okay, so now, so you'll go for next one, the next rotation. So the next rotation, you'll go for next rotation. So next rotation is the jag rotation. It is the jag rotation. Jag rotation. So in the jag rotation is same as the previous one. So what is the characteristics of this one means here? So in the zigzag rotation, so the same thing here, but so the element, see here, this x is the element. Let's say the x is the element resist. So now we got it is z. It is jag rotation. So z is a root node, and so the z as the child node, right side is y, and this y as say x as a right side. So let us say here, so there are some the child nodes, say it's a t1, and the z has got, say it is t1 and it's t2. Those are the child nodes of z. The t1 is a child node of z, and t2 is a child node of z5. So now the element you want to search is x, and y is a parent node. And the z is the grandparent. Okay, the y is a parent and z is a grandparent. So for this, in the z rotation, as I told that, so here, so now, so replace z by x. Replace z by x. Then, so make this y as a child of x. Then, so make the z as the child of y. So these are the operations you have to carry out. So now the difference between the zig rotation and jag rotation is So here the element you want to search, it is right side of the grandparent. Okay, it's the right side of the grandparent. So here is, so we say here is, so the x is the right side. It is a right side. So the right side. So the x is the right side. So therefore, so this zigzag rotation. So in the zigzag rotation, so the x is the root, and the x is a root. So x is a root. Then, so the y is the child of x, and z is the child of. Okay, so this is what you have to do. Okay, so the so the t2, that's t2 of the y becomes t2 of y becomes z child of, so the t2, and so and the whatever the values that is present in the there is, it becomes a t3. Okay, this t. Okay, So we'll, yeah, so please log in. We'll continue our discussion. The meeting could end within a 1